Muy buenos días, estamos en una nueva defensa de tesis doctoral en la Facultad de Ciencias Exactas. Esta es una tesis doctoral enteramente virtual. Esta tesis ha solicitado defenderse en inglés y se ha aprobado esa moción, por lo tanto, bueno, Matías va a defender en inglés. Pueden poner los subtítulos automáticos en la aplicación. Así que, Matías, muchos éxitos, te dejo la palabra.
Thank you. So, like he said, I'm Matías Sempé, and I will be defending my thesis. The title is Group Theory with Application to Quantum Field Theory in the Sitter. And this thesis was supervised by my advisor, Guillermo Silva. So, let's start. What's the sitter? The sitter is a maximally symmetric solution to the Einstein equation with positive cosmological constant, with the stress tensor is 0. And this is the simplest case. We can put up the sitter black hole also, but we will center ourselves in the most simple solution, that is without a black hole. The de Sitter geometry can be viewed as an induced metric on the hyperbolate. On the left, we have a Minkowski in +1 dimension respect to the de Sitter dimension, that is d, and on the right, we have the constraint. If we use the constraint on the left-hand side, we will achieve the de Sitter metric that we will study. Depending on how do we put the parameterization on the right, we will find different patches on the sitter. We'll talk a little about more in the next slide. And an important feature is that the isometry group is SOD, 1, which is very different from the compact groups and very different from what we know in Lorentzian ADS, where the group is SOD -1, 2. So let's move on. So the cosmological horizon. The cosmological horizon can be seen in the sitter when we write it in a static patch. In static patch, we can see that there is a horizon R equal L. So usually we take L equal 1, so the horizon is an R equal 1. So this horizon means that if we have Bob and Alice in the sitter, one on each side of the special sphere, and Bob trying to send a message to Alice, he will not reach her, except that Bob starts the message at infinite past, and Alice will receive an infinite future. So in concrete, she will not receive it in finite time. This is very different from what we know about the cases of Minkowski and ADS. In ADS, we can set a lag rate, we can always reach the boundary and back. But here, this doesn't happen. And also, if we take the full geometry, there are no boundaries. So every aspect of holography that we can think about having a boundary and having something defined there fails. We have no boundaries. And the most close thing that we can think as a boundary is a cosmological horizon. But we can see that even if we try to consider that as a boundary, this will be a like boundary. So this is more close to the Minkowski case in that sense. Other people try to do holography thinking about the infinite past, what we call sky plus here, and infinite future. Sky plus for the future, sky minus for the past. So let's move on a little bit. So we can see that the difference between ADS and ADS are a lot. So first, when we take the full geometry in the sitter, there are no spatial boundaries. So even the notion of charge is a little bit messy. Because if we want to do a charge, we have to go to static patch when we can calculate. But this charge will only live for an observer. So it will not be for the full geometry. Second, there is a cosmological horizon. This doesn't happen in ADS because L that we wrote before is imaginary. So the will be cosmological horizon is not in the real it's not in the real part of GTT. So GTT cannot be 0 in that case because the variables are real. Third, the isometry group is SOD, 1, which is very different from SOD -1, 2. For example, one of the main differences is that even if we graph a static patch that looks static, as the word says, The time translation in the global sense is a boost. So it's an SO1,1 that we will use later, actually. But in the case of ADS, the time translation is given for an SO2 that we usually descompactify when we grab the hyperboloid in ADS and we put it in, we descompactify the time, but it's an SO2 in the isometry group, a local sense. So this is very, very different. Fourth, we cannot apply our knowledge of holography because we have no boundaries. So even if we want, we have no boundaries, no spatial boundary. We can put a quantum mechanical system that will work as a dual. And if we take a static patch and take this as true, and we try to use this cosmological horizon as the boundary for holographic theory, it's very messy. You can see that in studies of celestial holography when they do that, and they have to start going to Carolian and start thinking because the boundary is like. So the like boundaries are very, very different from what we know about special boundaries. And the other possibility is take Sky plus or Sky minus. This can be achieved in Pimentel group, and those groups try to do something related to this, but it's different from what we will expect in ADS, for example. So let's talk about a little bit about the isometry group. The isometry group is SOD,1. This SOD,1 can be written as generators of the conformal group of D-1 Euclidean flat space. So we will not use a lot about this Euclidean flat space of D-1 dimension, but it's nice to see that we can recover an known algebra for us that we'll study when we do conformal field theory courses. So we have the generator series, and we see that here, and as you can see my mouse, the quadratic Casimir in general can be written as this. So we can use the quadratic Casimir to classify the representations. We will focus in these slides, in this and the next one, in scalar cases. Later, we will move up and try to talk a little bit more about spin cases. But for the scalar cases, we can see that the eigenvalue can be parametricized as follows. We can see here that we have delta and d-1 minus delta. This is delta shadow. We'll call it delta S in the future. Additionally, if we have a spin, there will be some S dependence if the parameterization. So, but we will always find this form of delta and delta shadow, even in fermionic representations. So, we will talk a little bit about what this delta means. So, delta classifies the type of representation. The principal series is one of the known cases where nothing very weird happens, but the delta is complex. Yeah, but the theory is unitary. The delta doesn't have to be real. Even in this case, the condition for unitary are simpler even, because delta and delta shadow are complex conjugate one from the other, and this simplifies a lot of things in the calculations. So in the complementary series, delta takes a value between 0 and d-1 over 2. And then we have complementary series we know from cases of ADS, for example. But in the exceptional series, this is not so well studied in ADS because, especially type 1, because type 1 is composed from shift symmetric fields. Shift symmetric fields are something that in ADS, for example, it doesn't get so much attention because the only field symmetric field that is unitary in higher dimension is the massless one. In the massless one, we have a shift symmetric, the usual shift symmetric that is with a constant. But in ADS, we can have tachyons that are unitary, and we will talk a little bit about them later. And in those fields, everything works exactly the same because they are unitary. We can do the usual inner product. We can do what we usually do, but the path integral is a little bit weird because we have to do a little bit of tricks. to do the path integral. We will not talk about the path integral here, but there is a paper, there are a lot of papers about this. So in the type 2, we have the usual gauge fields. So we usually call them discrete series. But they are a little bit special when we see the path integral in the sitter for the discrete series. So let's move on to the next slide. So before we continue, we will introduce one of the last elements on the group theory, that is the Harish-Chandra character. The Harish-Chandra character is the character of a non-compact group, and we will do this along the boost. It's the trace of the element that goes out the boost. This boost that we can see here is the time translation in static patch. So we will calculate this character usually in a sensible basis, as we say here. What we mean with sensible basis is that we can be very naive and says, okay, let's calculate the trace. What's the easiest way of calculating the trace? The easiest way on calculating this is to grab Hn functions of the operator D. The operator D is non-compact. This means that the Hn functions that we get will be delta unitary. So if we try to calculate the character using this in a very naive way, we will get an infinite. And this has to be regularized somehow. So it's important that if we want to do the calculation in a straightforward matter, we have to pick a basis that is L squared, for example, in Euclidean, but is the global basis, for example. The global basis work well for this. And we can do the calculation. Even in the thesis, we have the calculation for the dimension 2. In higher dimension, there are a little bit of subtleties. You have to take into account the generation, and this makes it a little bit harder to use this method. So maybe you have to use different methods, distribution, for example. So also, I'm introducing this, seems like very unrelated to what I did before, if we try to match the points, but I'm introducing this because it will appear when we do the path integral for the gauge field later. So let's continue. So continue with the introduction. I will talk a little bit about the conformally flat spacetimes and the primaries. So we know that the sitter is a conformally flat spacetime. For example, we can take the Poincare patch, and there we can see that it's a conformally flat. And in the HDS case, we can take the conformally patch for Lorentzian. In Euclidean, we can do the same. So at the level of infinitesimally, in the metric is conformally flat. So we are not talking about the topological that is different depending of the case. So here on the left, we have the conformally flat metric, and we can do a transformation that gets split because in a conformal factor and a Lorentz factor. And on the right, we see that we get a function that goes to the left of the previous metric. So this function is the conformal function is a conformal function that can be expanded into conformal Killing vector. Yeah, infinitesimally. So infinitesimally, we also have that these fields are conformal Killing vectors here. We have in the sitter 4, for example, we have 10 Killing vectors and 5 properly conformal Killing vectors. We will call properly conformal Killing vectors that we will talk about in a bit. So those one where the right hand side is not 0. If the right hand side is 0, this becomes the usual Killing equation. Also, the left hand side can be written as a Lie derivative along zeta mu for the metric. And the right hand side is we will get sigma later. Yep, with that too. So if we grab, for example, a scalar primary and we do the infinitesimal transformation, we will get what's on the right. This is what we will expect in flat space, and this is the obvious generalization. here the derivative here is a partial derivative because it's a scalar field. But we can put a covariant derivative and it will not change. So this is what we'll expect in the flat case. Well, we will call the gradient of zeta over d sigma in what we learn in differential, for example. So if we try to do the spinning primaries now, in the spinning primaries, we will have an additional Lorentz transformation here. So when we do the calculation that is in the thesis, the proof is in the thesis, we can see here that we get an additional 1 here. And if we do the same here, we will get an additional 2. Notice that the case before was a partial derivative here, but that partial derivative can be interpreted as a Lie derivative. So the correct way of doing it is with the Lie derivative here. And we can see here. In the Lie derivative, we can, as the metric is Einstein metric, and the connection is the usual Lecce-Bita connection, we can replace every covariant, every partial derivative in the Lie derivative with a covariant derivative and nothing change. This will not be the case if the connection was different. So additionally, this transformation doesn't stay in the gauge, in the Lorentz gauge. So we will see in a little bit of slices that this requires an additional gauge transformation if we want to stay in the Lorentz gauge. This is important because if we start with a gauge field and we do a primary transformation, the result will not be something that is only physical. We will have a contribution that come from gauge. Yeah, so let's a little bit move. So let's talk a little bit about more introduction, more properties. Well, we introduced it before that we have the conformal Killing vector equation. Yeah, we talked about a little bit about how the left-hand side is the Lie derivative of zeta mu over the metric, and the right-hand side is the conformal factor. We can see here how we normalized the Riemann tensor. And using this Riemann tensor, we can do some calculations and find that, for example, the one form associated to the conformal Killing, to the properly conformal Killing vector can be written, is an harmonic function. Yeah, and also is the one form is exact is the derivative of a function. So those functions that we have put here can be choose to be the embedding coordinates of the sitter when we will parameterize this, obviously. So and this span all the proper conformal Killing vectors. So what we are finding here is that if we know how we used it, the embedding coordinate that we used at first, we can get all the conformal Killing vectors easily. And we can apply everything that will come from here. So let's move a little bit. So why we introduced the conformal primaries before? The conformal primaries were introduced to use the ladder operators. At first, those two things seems very unrelated, but we will see now that this is not the case. First, we will start with an harmonic function in a maximally symmetric spacetime. Yeah, so we will parameterize lambda, the station value, as the following. So if we grab this, put it here, we will see that we can use the following operators d and delta shadow and d shadow to get new fields, phi prime, phi prime prime. We can see that this is exactly the infinitesimal form of the primaries. When one primary is defined with delta and the other primary is defined with delta shadow. So using this new field in the Laplace Beltrami operator, we can see that we get a delta prime and a delta prime prime, and we can see that the delta prime move delta plus 1 and delta minus 1. So we are constructing different solutions. So we are spanning all the discrete labels of delta in this case. When we talk about discrete labels, we can pick a little bit different cases, but usually from what we explained before, the sphere, for example, what we care about in Euclidean is all the delta discrete labels. So we can build all the discrete harmonic, all the spherical harmonics from here, and we will talk a little about in a bit of in one of two slides. So, and in Lorentzian, it will be a little bit more subtle. We will talk about later. But in Lorentzian, there are two cases that will depend if the theory is unitary or not unitary for the field that we grab. So, from here, we put the D and do the transformation. But delta is not something conformal in principle. We can see that here there is no necessity of having a conformal invariance. So delta is not the usual delta that we know that, but we can recover this limit. If we do the algebra, we can see that the right hand side goes that d minus do minus 2 delta. So if we, well, first, if we want to go up or down in delta, it will be by this, from what we pick as delta and what we pick as delta shadow. Yeah. So we talked about a little bit recently in the last slide that if we grab this equation and do this calculation, we can see that here we can put a delta that goes at d minus 2 over 2. This is the conformal dimension for a scalar. Yeah, and if for a bosonic theory in general, if we have the kinetic, usual kinetic term, we can deduce this also from the kinetic term in the Lagrangian. So there is a case when we recover the known results, but we see that if we don't use this delta, we will go up or down in deltas. So this is new. Also, in the scalar case, the transformation D with K gets the usual conformal algebra. Yeah. So because K and C will do a commute to a conformal killing vector. So this is why on the right hand side we have D. The Euclidean construction. We talked about a little bit before, but when we're talking about Euclidean, we are mostly focused on the sphere because in the case of hyperbolic space, the labels are not discrete, are more continuous. So it's we don't expand all the possible harmonics. So from what we talked about before, we can construct it. How do we construct it? Well, it's easy in the Euclidean case. In the Euclidean case, we can grab phi0 that we define as a constant. And using this constant, we can transform with delta equals 0 to the transformation, and we can build the first harmonic, and we can move up and build all the harmonics. So in this, we are building all the harmonics. Obviously, we will depend on the conformal killing vector that we choose. What's the other quantum numbers of the harmonic that we find? Yeah. So usually, unless of what we did with Guille, the easiest way is to grab the most simple conformal killing vector that doesn't change the other quantum numbers, and then when we get there, use the isometries to get to other quantum numbers in the theory. So at least you can find that there are other quantum numbers in the theory. So in the Lorentzian case, when we are thinking, we did mostly in this metric that we put here, that is the global decider, and this is the usual weak rotation from the Euclidean sphere. We can get two cases. We can get what we is usually called gauge modes. Those are the modes that are weak rotations for the Euclidean scalar case. So we can do the same. We have the constant, and with the constant, we build all the possible um, harmonics. But those are not unitary, the theory. So to get to the right-hand side, the easiest way is to solve the conformal case where delta is d minus 2 minus 1. This case, if we are in even dimension, this is an integer, and we can apply everything we did before solving in this case. In this case, things are way easier because we can grab, instead of the metric, we can do point parametric, solve it in point parametric, and then use the transformations. Or we can do it in this in the arithmetic universe coordinates, for example, and then use this transformation. There are a lot of possible conformal metrics that we can use to simplify the problem, and then start constructing all these cases. Yeah. So we can see also that this delta has a limit of up to where it can go up. It can go up to the conformal dimension. The conformal dimension, it will stop because D will be an isometry. It will be an isometry, an invariance of the theory. So with D, we stay in this harmonic, and we call it harmonic as the Asian function of the Laplace-Beltrami plate. A little bit more about the tachyons that we explain when we talk about the parameterization of deltas, and a little bit in the previous slides. So reminder that we will put a number when we will put coordinates. We're always thinking about global coordinates. I don't know if you can see this black square, but I will move it here. So the case of the tachyonic fields have a delta with a negative integer. It can be zero also. Zero is not a tachyon, but zero is a shift symmetric field in the sense that we can put a constant shift. In this case, the unitary solution is this phi n that we are putting here. This phi n is unitary only when the L that parameterizes the bigger quantum number about rotations is greater than the number n that goes of the absolute value of delta. So this is only the unitary modes. Otherwise, those are gauge modes, let's call it, because Q and P are not independent. So where we care when we talk about unitarity is this. But there's a little bit of subtlety in the following sense. We can also solve phi and find what's here. This is for the massless case. And in this metric, what we are putting in a very complicated way here is what if we solve the massless case in two dimensions, we will see that we have the right movers, we have the left movers, we have a constant that that is what we usually want to gauge away because we don't like it, and we have a time dependent. We grab the conformal metric in two dimensions, so we have a linear in time dependent, and this is not unitary on its own, but it can be combined in a complex way to get something that have a norm not zero. And we can think, what does this do? And we will see a little bit later that this thing can be used to construct right movers plus left movers using the isometries. So, yeah. So additional, the pure gauge modes transform in among themselves under the group, so there are no. The isometry group doesn't change the fact that you are in the unitary or non-unitary field. So we have the Legend Q modes. Those are the modes that we usually exclude when do calculations. For L greater than N, these modes can be expanded in P. Otherwise, they are independent. And we can see that if we do an isometry, we can see here that the L equal n plus 1 with an isometry becomes a combination of p modes, and the second terms here vanish. So what we are talking about, but to put it in an example, if we got the massless case and we grab, for example, the time-dependent solution, if we do a boost, we will get a right mover plus a left mover. Yeah. So well, we can do it in greater, but in greater this term would not be zero. Yeah. So here we have the property how the Q's are related to the P's. And L plus and L minus are written as follows. So, and we can try to apply ladders on tachyons, and we will see how they are rising and lowering. And we can see that if we have something that is unitary, we cannot rise here. No, sorry, here, because if we go up in n, if we start with greater L and a smaller n, and we start moving n up, eventually we get to zero because we will go from unitary to non-unitary. Yeah. So you cannot cross this. The D is something that will keep you in the unitary fields. In the other way around, if we start for a pure gauge mode, that is that have n greater than L, and we start to diminish n, we will not be able to get an unitary theory. Yeah. So the same happens from the Q's. So let's talk about how do we generalize this to the transfer vector case. We talk about later when we introduce the spinning primaries. In the spinning primaries, we talk about how if we do a spinning primary transformation, what we get is not in the Lorentz gauge or in the transfer gauge for this case. So we need to add a compensating gauge transformation. So what happens if we have to do ladders, for example? First, we will parameterize the solution to the Laplace-Beltrami operator as follows. And if we grab this, we can build these two ladders rising and lowering. And we see that here we have an additional term. This additional term is the compensating factor to stay in transversality. But this additional term cannot usually be erased. Can be erased in the case that A is a gauge invariance, because we can do a gauge transformation and get rid of this term. Otherwise, this is just a term that is added as an operator. So we cannot erase it. So if we do the commutator, we cannot do the commutator and at the end do a gauge transformation. We have to take into account all this and do the commutator with these two, for example, with the full operator. So the algebra and the Killing vectors. So the algebra is the same as always. We have things here. We can see that it repeats itself in the sense that we can pick the conformal weight as di minus 2/2. This is happen for the boson. Will happen later for the graviton, and get an invariance. So this is a fact that this is some things that we would like to happen. But there are some point we can recover the conformal weight. Otherwise, it will be weird that we are using the same infinitesimal form as a spinning primary and at some point not recovering what we expect from a conformal primary for a conformal theory. So, we will talk about conformal algebra. We are talking about in the conformal algebra, when you do a commutator between two conformal transformations, two primaries, you get an isometry. Usually this is called two commutator or two conformal give you a killing, the commutator on conformal with killing give you a conformal, and the commutator on killing give you a killing. Killing with killing obviously works, but conformal with killing and conformal with conformal doesn't work because we are added this extra term that to stay in the transversality condition. If we eliminate it, it works usually. This is what is done in Defensa, for example. But we want to keep this additional term so that we can use these ladders to construct all the transverse harmonics. So also, killing vectors have delta equals -1, and there are zero modes of the ladders. So we can see here the calculation, but this can be generalized, can have a generalization to spin 2. Yep. So before we move to the graviton, let's talk a little bit about what happened in the very particular case of 3 dimensions, in particular in the sphere. In the sphere, we can have the generators that are on the left. They are written in a way that resembles that the SO4 group can be written as the product of two groups. So we can write the two Casimirs. We have two groups, and we have two Casimirs, one for each group. We can put it together, we can put it in very different forms, but we choose this one. Yeah. So in this way of writing it, we will get that the first one is the usual Laplace-Beltrami with a constant that is referring to the Casimir, but we can shift the constant to get the Laplace-Beltrami. So you put a +2 here. And we get like a Chern-Simons-like operator. We know that the Chern-Simons-like operator square will get you something that is related to the other Casimir. And if we parameterize with solutions from here, we can see that it's exactly the square. Yeah? So later, I know the next slide or a little bit more later, we'll talk about what are AK mu plus minus. So we have what we did before. Here is a reminder, and we can think what happened when we use the conformal transformation with the other Casimir. Yeah. So we can think that maybe these ladders that go rising and lowering doesn't respect the additional Casimir that we worked. So if we take this basis, yeah, when we pick eigenfunctions of the C tilde, we can see that we can do exactly the same for both cases. In this case, it only goes up and down. So the new values when we transform are goes k to plus k and k to minus k. So k equals 0 is not in the spectrum. So we are getting something very similar to what we know that happens for a scalar case and for a massless scalar. In the massless scalar, what we know from several papers from Tarek, Gies, and Dio is that if we start with a right mover, we cannot go to the left mover using isometries. So one usually expect that this is the case for higher dimension, that we will case like a lower weight when we try to go from the left mover, we try to go down, and we eventually reach 0. And we can call this the lowest weight. And we can start from the left mover, go up, and we will get to 0. So we are getting like the highest weight and lowest weight on one side and another. Well, if you want to do this in vectors, you can do it with say tilde. Yeah. So this is not something that happened for higher dimensions. We found it here, but we cannot find in higher dimensions is an operator that works like this with the ladder. So this was one of the motivations to understand a little bit how do we get something related to this lowest highest weight that we think about in the massless case. We can do the graviton now. The graviton is just this, what we will expect as a generalization of what we did before. So we grab a symmetric spin 2 field, we hold the transverse and traceless condition, and we parameterize it like this. You can see that here there is a pattern because this 2 is the spin, and before it was a 1. So we can expect that for higher bosonic cases is 1 to solid, we will get the spin here. And the transformation will be quite similar to what we did before. The transformation will be the usual primary transformation subtracted with a gauge transformation, let's say. Yeah. Notice that here we are not putting an arbitrary constant. We are putting a very particular constant that is the compensating factor if we try to calculate the traceless and the transfer condition of D. So we fix this constant. We did that in the vector case before, using that this will strengthen the transfer gauge. So we can do the calculation. We will get the same algebra we did before for the other bosonic cases. We can see that here we have a conformal. The conformal delta actually works, and we are recovering something that Basilio found in a paper when he found that there is a conformal light symmetry. Okay, so the conformal light symmetry can be interpreted as this. This is the operator. And in particular, in that case, this additionally coincide with the partially massless field. So usually this m squared goes to 0. So we are in the strictly massless case. In the strictly massless case, we have the usual gauge transformation that is like the diffuse, but we can have a partially massless field that have a reduced gauge transformation. It goes like this. So A is a scalar, so it only works on scalars. It doesn't work on everything, like on every, how do we say it? On every vector. So like we did before. So this is a very particular case. So this is what he found for the partially massless case. We are looking at why he didn't find the algebra. Well, he didn't find the algebra because he need to add this additional term there. This additional term is what is spoiling the conformal algebra. This additional term, I mean the compensating term that goes to Saint the transfer case. And we said it before, we did a spoiler that there is a killing equation that generalize, and it's called killing stacker tensors. The killing stacker tensors are this one. We can act on the left hand side with a covariant derivative, contract with a covariant derivative, and we will get this one. This one have delta equal -2. Again, we see a pattern that if we generalize this to dimension to the spinning S, we'll get a spin here, seems like. And we get, again, that those are zero mode of the ladder. Yep. So this is just a curiosity. Now, we'll move to doing a little bit of quantization. We know how to construct all the Euclidean harmonics. We even know how we can construct the Lorentzian case even. By having one solution, and we construct all the possible solutions to the discrete series, to the discrete label. So we can do the quantization now. So let's start. We will do the Maxwell field. In the Maxwell field, we start with the action that is here. At some points, maybe we can put it in the way of a Shanks mill where the group is not abelian, but we will focus on the abelian case. So this has a Weyl invariant symmetry that we can do, that is just transforming the metric, leaving the A exactly the same, not constant, exactly the same. So if we do this, we can see that this is invariant. We can do that at the level of the metric. So setting the stage. So we will grab the action, pick conformally a metric with a conformal factor at front that multiplies everything, and we can do the Bayesian variance and get rid of the conformal factor. We will use here the Einstein static universe. We can think, why do we pick this Einstein static universe when we can pick, for example, the Poincare array? Well, the things goes as follows. If we grab the Poincare array, every generator is it have a spectrum that is continuous. Yeah. In this case, as the topology of the sphere, as the topology is a sphere, the labels of the spectrum when we get the quantum numbers will be discrete. And it's easy to manage to do the hit kernel calculation later if we have this case. So the Riemann tensor simplifies to what's on the right when we actually put L equal 1. And we get here the three sphere metric that goes as follows, as usual. So we can put the equation of motion, grabbing, we have the equation of motion is the contraction of the covariant derivative with f mu nu. We can start commuting things, we will get this. And we'll put the Einstein static universe, and we will additionally use the temporal gauge, where A0 IT is equal to 0. And a particular unsensible thing that happened for this gauge is that this gauge is not diffie invariant. If we do a diffie, the Lorentz transformation is conserved, but the temporal gauge is not conserved. So when we do a diffie, we have to do a gauge, an additional gauge transformation, so that we are back to the temporal gauge. So grabbing this, using the equation of motion, using the temporal gauge, we will get the gauge fits an equation of motion. Here, if we put the ansatz, that is the usual harmonic ansatz, stationary ansatz, we will get this equation. If we put the two on the right, we will see that this is a Laplace-Beltrán equation, and we can solve this. So, explained that a bit before, we will explain it again. So, we have the following Casimirs of the three sphere. We talked about before how those Casimirs can be constructed from the group. Here on the left hand, the C. C is a Laplace-Beltrami operator, and on the right hand side we still have something like a Hodge D operator, and one is the square of the other. So we can grab the eigenfunctions on the first Casimir that we can grab. There are a lot of papers. We used one from Shang. I know that there are methods for Gucci to construct this, but these are the simplest way to build them. Y, KLM here is the scalar harmonic, so we can use the scalar harmonic to construct everything. And we will get that these three are the three possible modes that we have for the three sphere when we see that the first mode is the derivative of something, so it's not physically. And we can combine S2 and S1 to have S plus minus. S plus minus are solutions to the C tilde here. Sorry, C tilde square is minus C. I forgot a minus before. So we can see that C tilde over this is 0. This is expected because it is a scalar, so it doesn't have right movers and left mover quantum numbers. C tilde is like a measure of the right moving of left moving. So this is why this is 0. And this is K plus, and this has one branch, one positive and one negative branch. So we have the expected orthogonality condition, and here we have the completeness condition that we will use in a minute. So we can grab the most general solutions that are the stationary function of time and the expansion over all the possible cases. When we here we choose actually what we will call A and we will call I dagger. This will be what we will expect in the quantization. We have put in here. So these are we were talking about in the next slide, but these are choosing A is choosing this way so that when we continue, we do the weak rotation to Euclidean, into South Pole. That will be the negative past. In this continuation, this function doesn't have a pole there. It's worse. It's smooth. So this is why we are picking A. This is the Bunch-Davies vacuum choice. And here omega k is K plus 1. And we get four possible, we get a set of four possible functions, or eigenfunctions, that doesn't meet some on each other. We can see this using a diffeo. We will choose the following Killing vector. We chose this one because it's the simplest one. This is a similar calculation, but not exactly the same. It's done in an old paper by Gucci, but and here's this one. The reason to using this one is that if we want to get another one, we can just do a different diffeo over this, a rotation, for example, and we will get the other. So the transformations that we do when we use this diffeo, as we talked before, have to get an additional contribution from a gauge transformation. We got the delta alpha. We can see it here. If we do the gauge transform, if we do the diffeo, it's a Lie derivative. And when we do the Lie derivative, we look at the temporal index, we will see that we get something like this. That can be gauged away using choosing this conformal transformation. So this is the transformation that we will do. Using this, we are still in the temporal gauge. So with the solution, the right hand side can be expanded solutions of this set. Yeah. So we can see that this is never zero, actually. Actually. And they do not meet. Only K rise or K lowers, but they do not meet some on each other. And another fact is that here this cannot go to zero. L is positive and K is positive in this case. So this cannot go to zero. So static from the ancient functions, as we did before, we can put a constant at front, and we will fix this constant using the inner product that we will write here. This inner product gets simplified because of the Einstein static universe, and we get this here. So we can get, if we put the stationary gauge, we see that this at the end is the 3-sphere L square inner product up to a constant that depends on omega. Yeah. So we can do the canonical momentum, that is the derivative respect to the temporal to the derivative of A in t. So doing this calculation, we get this, and we can construct the Hilbert space. We got Q and P, And we have to put here a projector to stay in the transverse because we like the transverse. These are the physical modes. So we are putting here is the transverse. So here we put a projector and we put the delta. This can be written like this with a delta here, and we can use the complete set property here. We do here, and using the projector and how it acts on every S, we can get rid of 0, and we will get this. Yep. So we can look at gauge invariant operator. That is the most known. Is the F. We here choose already A and A dagger with the usual algebra, and we choose the vacuum like this. When this, we will get this from here when we see how it goes in the time. If it goes down minus, it goes like this. When we rotate, and the transfer field can be chosen like this. We get a magnetic field and an electric field. So this is all for the canonical quantization. We saw that in canonical quantization we are getting mostly 4 modes to 4 sets that are solutions, and we do not see something like an edge mode or something weird that is longitudinal and appears somehow in this approach. Notice that we are not picking a static patch. So in static patch, things can be a little bit different because static patch has the cosmological horizon, and we can think of this like a boundary like, and we can maybe do something from there. This is explained more in a paper by Albert Law, in a recent paper by Albert Law, but we will not focus on that. We will not do the path integral and see that in the path integral we see additional contribution that we are not seeing in the canonical quantization case. So we start with the gauge, spin 1 gauge in abelian case. We will impose the following change of variables. If we do the change of variables, we are getting this new measure, and the action reduced to this action. This is a Gaussian action, so we can do the calculation. We can put here the Gauss contribution if you want. This is not necessary, but it's something that looks nice to show. Notice that we are picking an sphere in d+1 now, so we are not picking dimension d equal 3 from the start. This is something that is required by the calculation, so we will see in a minute why. But the calculation is the same for all dimensional up to this point. And if you do the path integral, we get the determinant on the part that is that come from the transverse, and we get this is part that come from the transverse, and here we get the Gauss contribution that is a boson, but it's go gas because it's a ghost. So, and we get zeta g that goes here, and this is like this. This can be put like this. So this is the full group, and here we are excluding the 0 mode from the calculation. Why we are excluding the 0 mode from the calculation is because when we do the parameterization before, if we put the 0 mode on of the scalar field, this doesn't change the AMU. So it's not a real contribution of the AMU. So the good calculation have to be done like this. So the partition function can be written like this, and we can do the logarithm. And here, this is we are putting a regulator here. That is important. And we are doing the hit kernel trick. Notice that one goes positive, one goes negative, because one is in the denominator. This one is in the denominator, this one is in the numerator. Yeah. So let's calculate the cost contribution. The transfer contribution will be exactly the same to subtle this. So we have to calculate the hit kernel. So we grab all the possible solutions here. We will put the Asian values. And notice that we are excluding n equal to 0, as we did before. The trace is primed because of this, that we exclude the 0. And the generation is given by this one. This is a nice way of writing it. Another way of finding this, but it's not so nice, will be using the Val dimension formula, for example. But this requires knowing the highest weight. So yeah, so we will pick this from the books and do the calculation. So if we replace what we took in the last slide, we will see that we will get this form. This is the expression that we want to compute. So we have to do a little tricks now. So the first trick is to complete the square here and write it as a Gaussian integral. If we do this, we will get this. Yeah. So we are trying to get something square here, so that we can use the Gaussian integral. If we do this, we get f. Notice that we are putting r. This Gaussian integral has a small imaginary third. We will see y in a minute because it's hard to see here y in this f. We got to resume it first. So, and if we want to go back, we can evaluate the Gaussian integral and we will get to what we did before. So this part resumes to this on the right. And notice that we have poles in the real variable for u equals 0 to pi and so on to pi k from k integral. So this is why we are putting this plus I delta here. So we can use this form. We write it like this. This is just moving back and forward the integrations. So we can compute first the t integration. We have two contributions. One big contribution here, and we have the contribution here, and we can do it. If we do it, actually, there is a problem. Why? Because in rate when t is large, this goes like a to the t over t, and this explodes. So how do we compute this integral? We do what physics do. So we take the imaginary, and at the end return to real d. So we will get this. Notice that we have a square root here. So we can use this now. So we can use the contour deformation as follows. We start with this red line, we deform it, and we will get the blue line. And when we get the blue line, we can use that there is a branch cut here to write it in a most simple way, where q is equal to a la minus u. Yep. So we can write it like this. And we can do the transfer contribution now. The transfer contribution is very, very similar. So here we have the Asian values, we have the degeneration, and we can evaluate this at the same tricks. So we will do a little bit faster now. So evaluating, completing squares and doing the Gaussian trick, we will get the same contribution with different values here and different f. F can be resumed to this. There's no trick. You can put this in Mathematica, and Mathematica will give you this. And we can do again the control deformation. Putting U equal to ET and tricks, and we will get this. And this looks very awful, but we know that we can put a character we will call edge character, and we can put a character here that we will call bulk character. And we can write it in this way. So this can be written with the F that go with the 2 contribution for each character. This is the character from a scalar in di-2 in di-1 dimension, because we are in di+1, and this is the character for a spin 1 in d equal in the full dimension d+1, and we will pick zeta g so that it follows, so they obey this. And here we can write it at the bulk, the edge, and we have to subtract 2 times the 0 mode. Yeah. So look that we in the previous some slides ago with the canonical quantization, and we did not see any contribution that looked like this. So this is telling us that we are not understanding something, that we are missing something maybe in the canonical quantization that we see here. Also, we can think that maybe when we are doing the Euclidean path integral, the Euclidean path integral is actually looking at the static patch. As we know, the weak rotating static patch is the sphere, and the weak rotating global de Sitter is the sphere. So at the Euclidean, we don't know which patch is taking at the Lorentzian case. So if we don't know if this is the edge, if we don't know if this calculation is looking at the static patch or is looking at the global patch. So some conclusions. We disclosed the representations from the classical point of view, the quantum point of view, with the canonical quantization, with the path integral. We see that there is some difference in this in edge quantization. We will be able to construct all the discrete modes in the Euclidean case from a constant. So we see a new method to construct. We actually clarified some misunderstanding the conformal electron formation reasoning from by Basili. We showed how this transformation appears in a very different way, but more clear, because we see that this is not a conformal transformation. This is a different kind. We can compute the path integral, and in the path integral we see how the SO11 class character appears. We get the additional contribution of the edge modes. So Euclidean calculation is telling us something Lorentzian, and this is very amazing. We didn't include it in these slides, but we additionally, to the work presented here, we did the Fourier quantum mechanics work when we do the scalar bosonization and matrix bosonization, and we were able to analyze the thermodynamics of the systems. But we didn't include it here as it will be 1 hour more if I start doing this. Thank you all. So, questions?
Bueno, Matías, empezaríamos con las preguntas de Dionisios.
Dale.
Bueno, okay, I'll also speak in English because we have it's the language everyone understands. First of all, yeah, congratulations, Mati. It was a very nice thesis, very deep, technically very, very strong, and also very impressive that you had 2 different subjects in one thesis, matrix models and fermion quantum mechanics, and also group theory and quantum field theory. This is each of them on their own is already non-trivial. So just to set the stage for that. And also good job with a nice presentation. So now I guess Yeah, just some questions. So going in the order of the slides that you presented, just clarificational questions that I wanted to ask you. So when you say that the decider group is different from the ADS group, you emphasized this a few times. And I wanted you to elaborate a little bit on that statement. Could you clarify their differences, their
Yeah,
main differences, from a more mathematical point of view rather than a physical point of view?
yeah. So from the mathematical point of view, for example, the maximally compact subgroup of the sitter is SOD. In the ADS case, it's SOD cross SO2. So this is different. This will cause some problems when we go to even or off dimension because of the number of the cartons. In SO4 and SO5 we have the same cartons, but in SO6 and SO7 we have the same cartons. But when we are doing this subgroup, we are in some cases eliminating one carton. So this is a different quantum number. So this will cause problems in some cases. Additionally, the sitter doesn't have time invariance. We can see here that if we try to make it time invariant, the time goes in a boost. This is very different from the time that goes in ADS, because in ADS you have SO2. That is the vector that goes in the throat of the hyperboloid. So this is another difference.
Is there a mathematical way to express this difference?
Well, the SO2 is compact and the SO11
Yeah,
is not
maybe
compact.
something about the topology of the group, whether it
The top,
allows.
sí,
So
yeah.
then, yeah, so let me follow this question. Does anything special happen in the case where D is equal to 2?
Yeah, in the equal to 2, both groups coincide. So SO21 and SO12 are the two groups of the Sitter and Lorentzian ideas.
But somehow the physics that you discussed seems to be the same in 2D, the differences from the physics side. So is there
Well,
a way to clarify that?
yeah. So depends on which one is the compact generator. In the Sitter case, the compact generator will be an spatial compact generator. This will be the SO2 and SO21, and the SO2 that is in ADS is the time-like generator. So one is the weak rotating from the other, let's say. Also, the
But
topology
if
is
you just knew
different.
the group theory properties, would you be able to distinguish? Does that imply something about which representations we should consider?
Um, so it will change, for example, how do we compute the character? For example, because the character
Yeah.
here is on the SO11 and the character in the ADS will be on the SO2.
Yeah, but from a group theorist point of view, we could compute whichever character we wanted. This is not, yeah.
Yes, true.
I guess one question related to this is when we say the ADS group, do we mean a single cover of the group or
No, it's a double cover of the group. So
or more? Yeah. So maybe this is that we have this
okay. So yeah,
universal.
when we talk about the group, generally, if we do this that we are doing here, the time is periodic in the group and ADS, but we usually, I do not remember the word, but we usually span this time
Yeah,
to
the universal cover.
multiple times, so we get
Right.
a real line
Yeah.
in T instead of the compact one that we will get if we do the group and we do the usual parameterization.
Yeah. And in particular, this will allow us to have certain representations that are bounded in ADS that we would not naturally have in the sitter, where we consider the single or double cover of the group.
Yeah.
Anyways, okay, so
Yeah.
that was one comment. Another, if we can go to the Penrose diagram of the de Sitter. Yeah, could you, with a pointer, maybe indicate, you told us that the SO1, 1 plays an important role.
Yep.
Could you show us how it moves points around in the Penrose diagram?
Yep.
So
We have one here, and the foliation are like this.
yeah, so the SO1, comma 1 is a vector field that moves points.
So we have these foliations.
Great. Yeah. This is the foliation. Okay.
So it goes. I don't know how I don't know if I can put a different color one here.
It's okay with the same color. So is and in the other diamonds, I think it bends in the other way. But okay, in the
Oh,
other,
here. Okay. Maybe I think I know where you're going. So
yeah.
if we go here, this will become from time-like, we will go space-like,
Okay.
and here will be the reverse. I think.
Okay.
So
Perfect.
it will depend on the patch if this time is time or is space.
Hmm.
So this is one of the problems.
Yeah. Perfect. Okay, so then let's move to the list of the representations you had
Sorry. I can't-
when you had the different deltas that were allowed with
Yep.
maybe it's the next slide.
I don't know how to erase this.
Before. Yeah. So here there's a curious thing that delta, well, it has these complex values, and then it has when it's allowed to be real, it lives between 0 and d minus 1 over 2, and then it's an integer.
Yep.
Could you give a bit of a feeling or schematic argument why what happens, say, if it's at d, yeah, minus 1, some other value outside this range?
Outside of this four.
What fixes, yeah, what is the condition that fixes these very special values for delta?
Unitarity and the positive norm. If we do the calculation, this calculation, this can be written something like the Casimir. I don't remember from the top of my head, from a function of p. This Casimir will be written from delta shadow.
Yeah.
So when we try to put a positive norm, we'll get how this
Yeah.
delta must weight, and the p will be limited depending if we have. By the way, if we are in the principal series, it's not necessary to fit p, but if we are in the other three cases, we have to fit p so that is go.
Yeah, so unitary, okay, so you're saying unitary will require this to be real and positive.
Yep.
But maybe don't erase it. But then still, why should delta only take integer values? Because delta times delta s, or yeah, so why should it be, if there's another term over here, is it positivity that fixes it to be an integer? Because reality alone, I can still imagine that delta could live on the real line outside these special values.
True. I mean, I know that it happens because I can do the calculation in Lorentzian and see that it's unitarity the theory.
Yes.
But at the level of the group theory,
Yeah. I think it's you sort of mentioned it's unitarity, positivity, and normalizability is the other one. It's the finiteness of the inner product that might be important.
so yeah. Also, I mean, usually when we start to look at p gets limited because of delta. We move delta so that the theory stays unitarity. So, for example, when we do the calculation, for example, if we do the character, we'll have something like this. But here, p is not whatever. P goes, for example, I think from the top of my head, from something
Yeah.
like this. So we put a limitation of p with delta. What else? So, see, so for the other case, delta, for example, is making is splitting the solutions in an invariant sector that go from P delta, I think is to minus delta. This is an invariant sector, and we have the sector that goes outside of P, that go from P delta plus 1 and P something like this. We can look at this from looking at Asian functions. I don't know what other property.
No, but okay. Yeah, let me not push too much with this.
Okay.
You have to get a feel for the, because it's a little peculiar. If you think about it from the ADS point of view, we are allowed any delta above the unitarity bound, and so it's, I think, an interesting difference. The other question I had on this slide is from a group theory point of view, again, the distinction between type 1 and type 2. Is there a way to refine what is their distinction without referring to the fields? So you
So in
separate
type,
type 1 and type 2, even though they have the same values of delta.
yep. So I am not too sure, but I think in type 2, for example, I know that we have a plus sector and a negative sector, but I think this is something that happens actually for the fuel exceptional series.
Maybe let me ask the question in a different way. Is there something about the say we do SO4,1 just for
Yep.
concreteness? Is there something about the SO3 content of these representations that is different? Like the spin?
Yeah. We have the spin. To get the type 2, you have to put the spin in SO4,1. And this will change the quantum numbers that you have in the tree sphere when you go below. You can have like we explain it later, but in the vector, for example, you have the right moving vectors and the left moving vectors using the Hodge D operator. That is the second Casimir of SO4. In scalars, this doesn't happen because in scalars the Hodge it doesn't have the form Hodge D. The C tilde we have zero quantum numbers because a scalar doesn't go right or left in this case, in this sense.
Yeah,
So
I
the
think
second Casimir
this
is
is
zero.
along the right direction. That they have a different that type 1 is usually for what we would call spin 0, where S is the quantum number of the SO3 subgroup, and type 2 will have S greater than or equal to 1.
Yep.
That might
Yeah.
Okay. Let's move on. I had a question about. So I thought the ladder algebra part was explained very clearly, actually. So I don't have any questions there.
Okay.
But I had a physics question relating that way you treated the Lorentzian versus the Euclidean Hilbert space of the Maxwell quantum field.
In the Maxwell, you mean in the quantum part?
Yeah, I thought this was very clear. The latter story I thought was very clear. So there was an interesting distinction. You did both the Lorentzian and the Euclidean, and in the Euclidean, the ghosts
Yeah.
played. If I remember, you emphasized they played an important role in the path
Yeah.
integral.
Yeah.
Yeah, but in the Lorentzian, I don't think you mentioned the ghosts at all.
No, because we are we are in abelian, so there is no necessity of adding the ghosts. We just have to impose the average of A, like I don't remember the name, but you can do the quantization without ghost because we are in the
Yeah,
abelian
so
game.
okay, but on the other hand, in the Euclidean, it's also an abelian
Yes,
theory. And so
but
why does your argument fail in that case?
so let's.
all I want is just a sense of what might be the distinction. I think you said it in words in your presentation, but I wanted to see, the essence of the distinction, why ghosts might play a role in one picture but not the other.
Well, maybe it's this, but when we are doing the Euclidean calculation, we are in the sphere. The Lorentzian equivalent to this sphere can be static patch or global patch. So when we are doing the canonical case, we are doing it in global patch. So there are not, for example, large Lie transformations in global patch. But if we will do this in static patch, we can have large Lie transformations. So these are longitudinal modes that make leaps on the boundary. That the boundary, we mean the cohomological horizon. But in the sense of the Euclidean calculations, we don't know if we are thinking, if the theory is looking at the global or a static patch. I think it's looking at static patch from what we saw. But maybe this is a difference. So why doesn't get this contribution? Because the longitudinal modes doesn't have a let's say, boundary to live on. Maybe this is what you
Yeah, that's an interesting idea. Yeah, okay. And then the final question, because I don't want to take too much of people's time, is although you didn't talk about it, I just wanted your own view if there is any link between the two parts of your thesis. Since they were technically different, but I just wanted your point of view. If there was any interesting links between the two parts that you had thought of during your
Yeah, I
PhD.
think there is a link that I didn't talk about. I think we discussed it sometime with Guille, that we found, for example, that in the martially matchless case, we recover, I think there's a lot of links. I will point out for me, the most interesting one. That is that in the, well, we did
Here,
here.
sorry, to be clear, I mean a link between the matrix model part of the thesis and the theory QFT part of the thesis.
Okay.
Yeah, it's a more. I want your philosophy. It's more a question about your philosophy. Yeah.
So in the sense that it's a path integral and the methods are similar, in the sense it's connected. In the sense that when we do the quantum mechanical case, we are putting Matsubara mode. So this is a compact, let's see, manifold because it's an S1. In those senses, yes, but I cannot see a deeper link. Some question that we have discussed a long ago with Guille is that maybe this is somehow related, that in the fermionic case, at large L, large N, there was a phase transformation, a phase transition. It will be nice to understand if we can get an enhancement of the symmetries in the phase transition, and we can get something like conformal. We can look at this theory of the real dual of the theory, because usually what we do when we think an SYK and IDS2, we see that the conformal is a limit of the SYK. It's not in the full SYK. The full SYK is not conformal. So this will be related to that, and the conformal things is related to the conformal transformation that we explained here. So in that sense, maybe related. I don't know. I don't see much, because actually we are doing the fermionic part of the ladders now with Guille. So maybe it's more related to that when we finish it. So
Okay.
I don't know. Yeah.
Okay. Thank you, Mati. I don't have any more questions.
Okay, so Giselle?
So thank you. I thought the presentation is really nice, and it puts the two papers, the ladder paper and the Edgemose Maxwell field paper, really nicely together, I thought. So that was really nice. My questions are like a bit from curiosity. So in the ladder construction,
Yep.
If you can just show us like some of the, any of these. Like you have negative deltas, and then you mentioned you can build positive norm and negative norm states throughout
Yes.
the ladder. Is there a connection with like positive deltas to positive normal? Is there some?
Yes, this happens.
And then what do you do with the negative norm ones? Do you still keep them as physical, or don't you
Yeah,
consider
they are
them?
physical in the Lorentzian case. The negative norm and the positive norm.
Okay, so that was a bit new for
But the
me.
same happens, for example, for the massless scalar. You can have the right movers and left movers, and we have positive norm and we have negative norm, because this is a problem of the norm. The norm doesn't have a defined sign.
Hmm.
Because
So
it's a Klein-Gordon norm, for example, for the scalars.
what is the norm for you here? Like you have the Klein norm?
I think I put it below.
Maybe I'm thinking of a different norm.
Let's see, where is the norm? Here. This will be the norm.
The Klein-Gordon norm. Okay, I see.
Yeah.
Yes. That's the
So
difference.
you can see it here, for example, in the Einstein static universe case, that if we put this solution here, if we put it here, we can see that if we put omega positive or negative, this norm will be positive or negative.
Mhm.
It will
I
depend.
see. Okay.
So in this
Because
sense, yeah.
I think if you look at the group theory norm, I mean, you didn't do it here, and that's perfectly okay. But like that they have different one for discrete series, a different one for complementary series, like those would be all positive.
Yeah.
That's why I was curious. And and when you write down the dimension for a scalar, the delta for a scalar, you have a very specific expression, d minus 2 over 2, but you have a particular scalar with a particular mass in mind, right here.
Yes, exactly. This is the
Yeah.
conformally coupled scalar.
Yeah, good. And so you would, like with these letters, you would only go between discrete series, right? Like you wouldn't go into
Yeah, in even dimension, yes. In odd dimension, no. In odd dimension, this become a half integer, so I don't know what happens there.
I see. Okay. Okay, I see. Yeah.
And in even dimension, discrete series of what we like, this is the usual integer.
Yeah. And just out of curiosity, like with the character computation, I am happy with the dilatation, what you call the boost basis, but have you tried any other bases? Like, do you have any feeling what becomes really difficult?
No, I mean, the problem is that you can use whatever basis you want. For example, we can take a static patch. For example, if we take a static patch and we diagonalize this boost, we can do it, but we have to be very careful because you have to add a distribution there so that these things get regularized. But if you get, for example, let's say con Poincaré, it's the same. You have to pick a form of regularization of this. Put a distribution there. I don't know what with. I mean, if you grab a static Einstein static universe, I think this has no problem. For example, because the quantum numbers are discrete. But if the quantum numbers are a continuum spectrum, I think you will have this problem of the delta zero, and you will have to be very careful in the calculation.
Yeah, so nice. Thank you. This is all.
Thank you.
My
Nico, No se te escucha.
¿Está Nico?
No se le
No
escucha.
escucho nada, Nico.
Fíjate en audio.
¿Ahora me escuchan?
Sí,
Ahí está.
¿Ahora me escuchan? ¿Hola?
sí, sí, sí.
Ho- ¿Ahora sí?
Sí.
Ah, bien, bien. Ok. Entonces, I did a lot of calculation and questions in the previous stage during the corrections, so I don't have many questions to do. The first one was regarding the second line in precisely this equation you wrote here, but now I see that you clarified that on the bottom right, so that's okay.
Ah, here, okay.
Yeah, because I mean, you are putting names to the first parenthesis, to the second, and then there is this second line that had no reference, but now I see that you wrote it there. Another question was about the norm. So you're using the Klein-Gordon norm even for scalar modes, I mean, I suppose, right?
Yes.
Okay. And then I have a general question, which is, I don't know, it's about the context of all this calculation. And it's the following. Do you have any insight or any I don't know, naive expectation about which of the representations of the Sitter group have to be realizable into fields? Because in Poincaré theory, if you have the Poincaré group, only some of the representations of Poincaré group are realizable into fields. Are other representations that I don't know, people say that they represent extended objects and you cannot write them as fields. So here, do you have any expectation about that?
I don't, I don't know. In principle, for example, there is a subtlety. I think I talked with you about this in chatting. But for example, when we are using the calculating, for example, the quantum contribution to the tachyons that we talk in the thesis, it's a little bit subtle. How do we interpret it at the quantum level? Because you can do two things. You can, for example, let's pick delta equal -4. You can, when you do the computation in the path integral, you have to do the determinant that is written here somewhere here. You have to do compute this determinant with a mass with a plus here. You put this with a 0 here. We have to compute this, but what will happen is that the deltas that are over this negative n, negative 4, will contribute will have a positive Gaussian, like a to the plus x squared, and the delta at the fields and every other part that contributes with the negative Gaussian. So when you take on the quantum case for the tachyons, you have to be very careful with this. If you grab this part that contribute from what is below the delta and twist the sign of the norm so that it contributes at the quantum level or not, this is maybe something related to your question in the sense that at the quantum level is a bit subtle. How do we define the tachyons and if they can be measured in the sitter actually in our universe or not? Maybe this is related, but I don't know other fields that are weird like this. Maybe they are partially matchless that I talk about a little bit, that are realization of the linear contribution of to the Einstein action. This realization get a reduced gauge symmetry, and I don't know if this can be measured or not. If the graviton is strictly matchless in a universe or is partially
But
matchless.
all of this is at the level of fields. So
At the level
these
of
are
fields,
all
I don't
fields.
know.
These
Yeah,
are all
better
fields.
question.
The question is if you can expect some of the representations of the de Sitter group not to be writable at all as a field, as an operator acting on something that depends on the coordinates. And this is
No, I don't know if that happened. I
okay.
am not sure.
Okay.
I mean, for example, I don't know what it's a very subtle question. For example, let's think a little bit. For example, sometimes in the sitter for the exceptional cases, it happens that if you do the canonical quantization fails in the sense that the theory is not local. Maybe this is what you are thinking
That
about.
could be. Yeah.
For example, if you grab a massless scalar in the sitter 2 and you do the canonical quantization, you will see that when you put P and Q and do the commutator, you will expect a delta, but you get a delta plus something. but plus a
Okay.
constant. So
Okay.
this is not local. So the theory is not local. So you have to
No, the
find
question
a local
is
theory.
the question is motivated in the following: when you are at the laboratory scale, you don't see the overall curvature scale of the universe, so you may confuse your symmetry group with Poincaré, and so you will explore the representations of Poincaré, and you will say these representations are writable into fields, and these other representations are not. And then now you can embed that into the whole de Sitter universe representations. And I don't know if those which are realizable into fields in Poincaré are the same which are realizable into fields. I imagine they are the same which are realizable into fields in the whole de Sitter case, and the representations which are not fields of in the Poincaré case, maybe they simply do not exist in the Sitter, and that's why they are not realized in nature. I don't know. That's why it's the question.
Maybe
It's okay. I mean, you don't have to
let's
know it. It's just a question.
no, but maybe you are thinking if I grab the representations, I can do, for example, a non-Wigner contraction and go to the representation of Poincaré.
Mhm.
And you will see that a lot of different representation in the sitter go to the same representation in Poincaré.
Ah, okay.
So
Okay.
when you try to measure things in Poincaré, you don't know what you are measuring in the sitter because it's very subtle. It's a little bit of this L squared that you're taking to infinity to infinity.
Mhm.
So in this sense, actually, for example, you can see it for supersymmetry. The most everything wants this, but you can grab Poincaré. In Poincaré, you can get supersymmetry. You can put the Majorana fermions. You can put
You
the
can do
Majorana
whatever.
gravitino. Do the whatever you like. Any quality.
Probably
Super
the
symmetry.
reason because some of the representations of Poincaré are not realized in nature is because they cannot be embedded into a larger space-time like the Zeta.
Well,
Okay, that's
if you try to do the gravitino in the sitter, you will see that you cannot put it Majorana. I mean, in the usual action at least.
okay.
So why is this happening? So this is maybe what related to your question. It's not obvious
Maybe
that the representation match one-on-one from the sitter to Poincaré.
no. Okay, I don't have any further question. Thank you.
Thank you.
Bueno, si no hay más preguntas, lo que voy a hacer ahora es parar la transmisión de YouTube. So I'm gonna to stop the YouTube transmission. Arranco la transmisión de YouTube y arrancamos.
Entonces yo tengo que ahora leer
Sí,
el
si
texto,
tenés el dictamen, ¿no? La parte de arriba,
el
que ven que
dictamen.
se superponen cosas.
Bueno, entonces voy a empezar. Me da mucho placer aprobar la presente tesis con mención especial. Felicitaciones. Y ahora voy a leer el dictamen. El trabajo de tesis, teorías de grupos con aplicaciones a teorías de campos en Defensa, presentado por el licenciado Matías Nicolás Sempé. La tesis es oportuna ya que las representaciones de las series discretas de De Sitter en el contexto de la teoría cuántica de campos están mucho menos exploradas en la literatura. También nos gustaría mencionar que la tesis explora dos temas técnicamente y conceptualmente distintos, a pesar de lo cual lo hace Matías con un nivel apreciable de profundidad. Por otro lado, está técnicamente bien escrita y clara la tesis, lo que la convierte en una contribución a la literatura que resultará valiosa para la investigación futura. En base a lo expuesto, este jurado aprueba la presente tesis con aprobado con mención especial.
Gracias.
Sí. I just read in Spanish what we agreed in English.
Bueno, ¿quieren decir unas palabras? Matías, Guillermo.
No, gracias. Esto bueno y no sé, no tengo muchas más palabras.
Bueno,
Guille.
yo felicitarlo a Matías, que la verdad que trabajó un montón y es una persona muy motivada. Maybe I should say it in English. So I would say to congratulate Matías and say that he was all the time a very committed student, working on looking for references, discussing, very motivated during the PhD, and trying to work together with other students, and trying to make a group and join the people among themselves. So nada, Mati, congratulations, felicitaciones. We are happy that you finished, and now you will be starting a new period of research, more on your own. And bueno, I wish you the best. What can I say?
Yeah, thank you, Guille. Well, I couldn't do the PhD without Guille, actually. So I will be still in first year otherwise. So a lot of discussion with the group in general, with Nico, with Guille, with Dio, Gisem, everyone. So I'm very happy, and thank you all.
Bravo, congratulations.
Congratulations.
Congratulations. Giselle, a few words?
Yes, so congratulations to all of Life and Matías. It looks like a really nice trip it was for you both along the way, the whole PhD. Like the thesis showed that. And it was a pleasure to read it and to listen to the presentation. So well done.
Thank you.
Yes, and thank you to you two referees. Bueno, Nico is a close friend, so for you for accepting to evaluate the thesis. So thank you.
Bueno, entonces, muchísimas gracias a todos los jurados. Thank you very much to all the jury. Vamos a dar por terminada el acta de hoy, la defensa de tesis.
Luciano,
Sí, decime.
déjanos por favor abierta el acta porque como estábamos en computadoras diferentes, ni yo ni Guisem pudimos subir la firma.
No hay problema, el acta está abierta para cuando lo
Ok.
necesites, ¿no? O sea, puedes entrar siempre. No,
Ok,
nosotros no,
perfecto.
¿sí? Así que no hay problema por eso.
Ok.
Muchísimas gracias a todos. Terminamos una nueva defensa de tesis doctoral. Los esperamos el lunes para otra, el martes, el miércoles y así hasta el 18 todos los días. Así que por suerte se siguen recibiendo, eso es lo bueno. Eh, Así que bueno, muchísimas gracias. Damos por concluido el acto de la defensa doctoral del licenciado ahora doctor Matías Sempé. Ya
Vale.
hablé con vos, ya quedamos, en breve te mandamos el certificado, así
Dale.
que listo. Muchísimas gracias. Thank you very
Gracias.
much.
Luego.
Thanks all.
Adiós.
Thank you very much.